With MATLAB Multibody Dynamics, we're going to model a hollow rotating beam. Look at the figure next to you. It shows the hollow beam we'll create. The beam spins in the vertical XY plane, with its hinge and rotation centered around the Z-axis, which points directly out of your screen. We've already set gravity to pull downward in the mechanism configuration block, aligning it with the negative Y direction. The hinge is a sleek, frictionless rotating axis. The beam is solid with these dimensions. It is made of aluminium. We're starting with the program visible on your screen. This is how the beam looks like in the Mechanics Explorer. Now, we're about to expand it to a rotating hollow beam. Here's how we'll get there. First, as part of the preparation, we need to measure the beam's mass and its inertia matrix. To ensure smooth communication between Multibody Dynamics and Simulink, we add 2 converters and use 2 displays for output. Hitting run, we see the results. Remember, these moments of inertia relate to rotation around the fixed hinge point. To form a hollow beam, we need a second beam. Copying the first beam, we adjust its dimensions to reflect a wall thickness of 1 centimeter. MATLAB dynamically calculates the mass and inertia moments based on this geometry. We choose white to color the second beam, making it easy to distinguish. Its frame aligns perfectly, and the configuration is done. For now, we link this beam to the world frame, measuring its mass and inertia just as we did before. Let's note the values we found on the screen. In the Mechanics Explorer, we observe that the first beam rotates while the second beam maintains its fixed horizontal position, exactly as expected. To get the second beam rotating, connect it to the first beam, run the simulation, and the 2 beams unite, resembling a hollow beam. But there's a catch: the masses are added together. For a true hollow beam, the inner mass needs to subtract from the outer mass. How do we fix this? By giving the second beam a negative density, a clever trick in the engineering toolbox. While negative density doesn't exist in the real world, it works perfectly here, subtracting the masses and moments of inertia. Engineers sometimes call this technique Boolean subtraction. It's simple yet powerful. Once more, using the inertia sensor gives us the mass and moment of inertia of the hollow beam. Let us see the beam in action. In the hinge settings, we enable the position option, which tracks the rotation angle. The resulting graph reveals an oscillating motion. Using cursor lines, we measure the oscillation period and jot it down. We'll need this value for further analysis.
There's another way to model a hollow beam, and it's particularly handy if you're not focused on creating a highly realistic visual representation in the Mechanics Explorer. The trick? We'll work with a solid beam and assign it the mass, center of gravity, and moments of inertia of a hollow beam. In this way, the solid beam mimics the hollow beam in terms of its dynamic behavior. Let's pick up where we left off. The displays present the previously determined mass and moments of inertia for the hollow beam. We have also added the position of the center of gravity. You can easily view it by enabling Center of Mass in the Inertia Sensor block. If you want to see the center of gravity in the Mechanics Explorer, here's how to do it. Currently, the inertia matrix refers to rotation around the fixed hinge, which is attached to the end of the beam. However, for the next step, we'll need the moments of inertia relative to the hollow beam's center of gravity. Don't worry, this is just a couple of clicks. Simply select Centered Inertia Matrix in the Inertia Sensor block. Here are the results. For a slender beam, the z-value may be computed using this formula. At this point, we no longer need the second beam. Instead, we'll manually transfer the displayed values into the first beam. Here's how. Click on the beam, select Inertia, then set the type to Custom. You can now enter the values directly. Note that only the z-component of the moment of inertia needs to be entered. Now, you might think it makes sense to input 0.5 meters for the center of mass. However, if you do that and check the Mechanics Explorer, you'll see the center of gravity isn't positioned correctly. Resetting the value to 0 positions the center of gravity at the middle of the beam, exactly where it should be. To confirm everything works, we'll run the program and check if the inertia sensor accurately measures the values. And fortunately it does. By measuring the oscillation period in the scope, we find it closely matches the previously determined value. This reassures us that our approach is on point. Thanks for following along, and we hope to see you in the next video.